Welcome back, everyone. Today we're going to be going over time complexity, and specifically big O notation as a method of representing time complexity. So I'm going to start with explaining a little bit about what time complexity is. So when you have a given function or method, it's going to take a certain amount of time to run, and a way to represent how long it's going to take to run given the amount of input that you pass into the function as, say, a parameter is represented through big O notation. That looks something like O of n, and it might be O of n squared, O of 2n, O of log n, but that's going to represent the relationship between the amount of input and the runtime of the function. And there is a mathematical way to find out. It's not really mathematical, you pretty much just go through the code line by line and you know what to count and what not to count. And the runtime is basically calculated based off of what is put into the call stack. Now the call stack is something that holds whatever functions are currently being called. So if you call one function, it's going to enter the call stack, and there will be one function in the call stack. And then when that function exits, it will be removed from the call stack. But let's say you have a function that calls another function. That function is going to get called, added to the call stack, and then it's going to call another function, and the first function hasn't complete yet. So now there's two functions on the call stack. And so the amount of calls that are on the call stack is going to be counted towards time complexity. So a few things that aren't counted would be expressions and variables, because those aren't added to the call stack of any kind. And even if you're initializing a variable, that also doesn't count. But method calls are counted and loops are counted. So that's important to know, is that a while loop or a for loop, those are considered calls to a function. So if a for loop runs 10 times, it's going to be adding 10 to the time complexity. And any method call would add 1, considering that that method didn't call any other methods. Now I'm just going to show you guys an example of how you would take a simple function and get the time complexity just based off of looking at it. Okay, so big O notation. So I already explained briefly what it looks like, just O of n, and that n expression within the parentheses is going to change based on what something is. So let's take a regular function. Let's say you have a function that, just prints whatever variable you passed. So this function, this function is going to take n, and it's going to print n. And so let's say you passed f of 1000, it would print 1000, and yet it's only going to run one time, because there is no runtime that is based off of the variable pass. So whether you run 1 or 1000, the function will run print line, and then it will exit the function. Now, let's say that you had, within that function, you want to print the word hello. You want to print it n times. So just imagine that's a for loop that runs n times. Now, let's say you pass 5. This function is going to run a for loop 5 times and print the word hello 5 times. And so this time complexity, the runtime is going to be 5 for whatever number you pass in. So if you pass 1000, it's going to run 1000 times. And so this is an example of a relationship between the input and the output, which can be seen as O of n. And this is considered a linear time complexity that I'm going to go over briefly. But for now, this is how you understand big O notation. And if you want to visualize it right here, we have the function call. That's what this line is. And here we have a for loop, and this will count towards the time complexity, and that's going to be n, because it's going to run n times. This line is constant, it's only going to run one time, and then this is exiting and exiting. And so technically, if we were considering a print line to be a constant, this would be O of n plus 1, which would still be O of n, because we drop constants, because, let's say n is equal to 10,000. 10,000 plus 1 is not much different from 10,000. So as you approach infinity, the constants become insignificant compared to the output. So we drop constants, and this would be considered O of n. Now, we're going to go through some of the most common examples of time complexities, and the most common one, or the most simple one really, is going to be constant time. And notice that usually it will have O of n, but in this case it's O of 1, and that means that n does not have any effect on a relationship with the amount of output and the runtime. And so an example of this would be, let's say you wanted a function that returns the next number. You want to add the number. This is a pretty useless function, but as are most constant time functions, but they're usually used for repetitive convenience or readabilities. Like if you wanted to, instead of having to type out system.out.println every time, you could just make a function that simplifies it to just println. And then it just does that. It doesn't call any other functions, it just prints out the message. But here we have something that's going to return the next number. So you call this, you pass, let's say 10, it returns 11. But let's say you passed 1,000, it would return 1,001. If you passed 1,000,000, it would return 1,000,001, but it's not running any more or less amount of times based on the input. So even if you pass 1,000,000,000 through, it's only going to run one time. That's why it has a constant time complexity represented as O of 1. Now I'm going to move on here to probably the most simple representative time complexity, that is linear time, O of n. And that basically just means that whatever number you pass through, that's how many times it's going to run. And so a simple example of this is if you wanted to create a function that would print an array for you. So you have an array with 5 elements, and you pass it through here. It's going to run this for loop 5 times and print out each element. So important to note here that when you pass an array, usually n is considered the length of the array. So the length of the array is the input, not the elements of the array. And one of the reasons for that is because mathematically only the length is being used in this, and the array element is just being printed out. It's not actually being factored into any expression. So n is the length of the array passed through here. So let's say you pass through an array with 20 elements in it. It would print 20 times in this for loop that would run 20 times. And so that's linear time, because exactly whatever you put through is going to be the output. And let's say for some reason you wanted to print each one twice, and you wanted to do it stupidly like this, because no one would ever do this. But now you have 2 for loops that run n times. This is still considered linear time, but instead of O of n, it would be O of 2n. However, if this was a question on a test, it would still be considered O of n, and that's because we drop constants and coefficients. So let's say we added another for loop that ran 10 times. So now every time you run this, it's going to run the length of the array passed through, the length of the array again, and then 10 times. And so this would be O of 2n plus 10, because 10 is constant and unchanging, unaffected by the variable passed through. And then 2 times the variable passed through, because there's 2 separate for loops running that many times, would be O of 2n plus 10. And this would still be considered O of n. And in big O notation, the reason that we drop constants and coefficients are because as that number grows towards infinity, they become insignificant. We are only looking at the rate of growth, not the direct output. In the case of big O notation, you can use it for looking for direct output. Typically, it represents the rate of growth. And I'm going to pivot over to a visual example of this. And here are all of the most common time complexities represented on a graph. So we have constant right here, represented as this red line, and that's basically just going all the way to the right and all the way to the left without changing, because as n approaches infinity, the runtime is not changing, and that could be anywhere from 1 to whatever. As long as it's unchanging, even if it's a high number, it will become insignificant as n approaches infinity. And now we also have, we'll make this actually linear. Well, let's just get rid of the complicated ones for now for terms of simplicity. this is going to be the ones, these are the ones that we've reviewed so far, linear and, constant and linear. And linear is represented by this because the slope is constant, right? So the slope is 1, and that's a constant number. And so even if we also had 2x, it is still considered linear because the slope is constant. It is not increasing as an exponential function would, or rather a quadratic function. And this does not have a slope really, it has a curve. And that's why this would not be considered linear. But these are both considered linear, and even if we had the latest example, plus 10, it is still linear. And so this is why we drop coefficients and constants using big O notation, because they become irrelevant as you approach infinity. Now before we leave this graph, I'm going to show you the graph of the next time complexity that we're going to look at, and that's going to be y of log x. And you don't exactly need to know what log means. I'm going to explain it in pretty simple terms for the purpose of simplicity, but it's important to see exactly how this line is graphed. And you can see that it's very little difference between constant, and that's really a really good thing for developers to know, because this is going to be the second best case time complexity, and oftentimes actually better than constant, considering that constant could be up here. But generally, if you have a relatively advanced but not super advanced problem and you can make it a logarithmic time complexity in a function, you've done a great job of making that efficient, because it is right next to the constant time here. So it's just about the second best and honestly almost equivalent, but with so many more advanced possibilities. And so now I'm going to show you the logistics of the logarithmic time complexity. Okay, so now that we're dealing with logarithmic time, I'm going to explain a little bit about the log expression. So we'll just say log of x in this case, and log without any base, and the base would be represented like that, where b is. This is going to be the base of the log. So log, when there's no base expressed, is going to be assumed to be 10. So this is technically log base 10 of x. And this is going to return how many times x can be divided by 10 until it reaches something less than 10. And that's a really simple way of looking at it. I'm sure somebody else could explain it better, but for this, that's all you really need to know. And we're going to be using examples of log base 2 of n, because that's the most simple. And that's basically saying until n is less than 2 divided by 2, and how many every times is the log. So let's say that, so log base 2 of 16 is going to be 4, and log base 4 is going to be 2. And I'm going to visualize that real quick. So log base 2 is going to divide itself by 2 once, and that's only one division. So log base 2 is going to be 1. And so let's say you have log base 2 of 16. Well, that's going to go to 8, and then 4, 2, 1. That's 1, 2, 3, 4. And so that is going to be 4. Now, let's go and jump really far forward to 1 billion. Okay, so the log of 1 billion, just imagine that I have drawn all of that down, is going to be about 29. It's either 29 or 30. So we've gone from 2 to 16. Nope. We've gone from 2 to 16, which is, times 8 difference. And we've gone from 16 to a billion, which is like 100 million difference, almost. Multiplying it by 100 million. And we've only multiplied the output by, 7 or 8. And so you can see how the large difference between these two, this would be the second best case scenario for a function. So if you can get a relatively complex function to have a logarithmic time, which usually can't, but in the cases that you can, it's a really good use case. And so that's why this is really important as a time complexity for your functions. We're going to look at log base 2 time complexities, which again, the base is going to be considered a constant or coefficient in this case, and so we're just going to drop it. So log base anything is going to be a logarithmic time complexity of O log n. And so this is the most simple 3-line version that you can have. This is a loop that is going to run while a certain number that might be passed through a function or set earlier is greater than or equal to 2, and it's going to divide that number by 2 and reassign it to itself. So this is the example that I already went over. If you pass 16 into this, it would run 4 times, and if you passed all the way up to 1 billion, it would only run 29 to 30 times. And so this is a really good way to still have the runtime linked to the inputs while having such a small correlation between the two, considering that it is very inelastic. It only moved up to 29 to 30 with 1 billion inputs. Now, if you would like a more useful example of this that would actually return something, you can manually create a getlog function, which I'm sure there is already a implemented function in Java or Python or whatever language you're using to do this. But if you wanted to redo it to see exactly how it works, this would be a logarithmic time complexity. So we have this function that is run, and it takes the integer number, num, and then we initialize, once it's run, a log count. And this is going to be the value that we return at the end that's going to represent the log base 2 of whatever number is passed. So that's the utilization of this function. And here we have the same thing that we have up here. While the number is greater than or equal to 2, divide it by 2, reassign it to itself, and increase the log counter. And so this log counter is basically just keeping track of how many times we are able to divide that number in 2, which is exactly what the log base 2 of a number would be. And then it's going to return that number. And so you could pass any number through here, and it would return the log base 2 of that number. And it would also, whatever number it returned, would also represent the amount of times that this function was run. And you know that because the log counter increment is inside the deepest level of it. It's not just inside the function, it's inside the while loop that is also inside the function. Now, this is using iterations. Iterations meaning we have a loop that is iterating over and over and over again and keeping track of that iterations. Now, if anybody is, for the people listening, if you are not familiar with recursion, you're going to get a little bit of an introduction into it today, but I would strongly recommend going and watching my other video on recursion, because recursion is quite a deep concept. But for anybody who does not know what recursion is, it's basically a function calling itself. And that can get pretty complicated, but we're going to keep it pretty simple for right here. Later on, you will need to have a deeper understanding of recursion to understand the more complex time complexities. But right here, we have the same thing. We are initializing the log counter first, because if you initialized it inside the getlog function, I'll show you exactly why that's a problem. We have an if statement instead of a while loop that says if the number is greater than 2, increase the log counter, divide the number by 2, and return getlog number. Now, this is using recursive return statements where it is returning a call to itself. And so here's the problem with initializing the variable within the function. It's going to call itself again, and the log counter will be set to 0 every time this is called. And so the log counter will only ever be 0 and 1, and that's why we need to initialize it outside of a recursive function. Whereas if you're using iterations, you don't need to do that. You only need to do it outside of the iterating loop. But here we're initializing it outside, and it's going to return the getlog of the number. And so what this is going to look like is, let's say you passed 8. Well, 8 is greater than or equal to 2. The log counter is going to increase to 1. And then 8 divided by 2 is 4, and num is 4, and it's going to return getlog 4. So then it's going to run again. 4 is greater than or equal to 2. Increase the counter to 2. divide it by 2, that's 2, and it will return get log of 2. Same deal, increase the counter to 3, and now it's returning get log of number, and it's going to pass 1, and it's going to go to the else, which is going to be log count minus 1. And so that's going to return 2 all the way back up to the original function. And in this case, we don't actually have to do the minus 1, so we're just going to keep it like this. We're just going to make it simple. It's going to return log count. So this is a little bit difficult to conceptualize, but basically when you have a recursive function, it's going to call the pre-recursive work that comes before the recursive call, how many ever times it's going to, and then it's going to call that many times the post-recursive work, which would be the returning. But in this case, technically the return statement is the post-recursive work. So the get log with the parameter 1 is going to return 2, which makes 2 return 2, which makes 4 return 2, which makes the original called function return 2. But in this case, it's actually going to be 3, so those would all return 3. Now, this is an example of the way that you could use iterations for a logarithmic time complexity, or an example of ways that you can use recursion. If you did not understand that recursion concept very well, I would not recommend continuing through this video without going and understanding recursion first, because some of the other time complexities are best understood through recursion. And recursion is, like I said, a pretty deep concept, so I will be posting a video on recursion explaining it in depth, and hopefully that will help with the rest of this video. Now we are going to move on to the more complicated time complexities, and as I've noted here, that everything past this point is pretty useless for simplification purposes. And I only say that because to make use of the larger time complexities, you have to have quite an advanced function, and I'm not going to get into that to explain that right now. I might make a separate video on those. I'm definitely going to make a separate video on the quicksort method along with the merge sort and bubble sort method. But for now, we're just going to use simple cases of this, and so I'm going to start with a different version of the getLog function. So here you have the getLog function, and it works the same way that it did. So here you have the getLog function, and this function is actually not going to return anything, but in the function itself, it is going to increase the log counter, and the log counter by the end of the function will be the log of the number passed. And so it works the same way as the method before, and here, so this has a logarithmic time complexity, and right here is going to have a quasi-linear time complexity, and that is because it is running as a for loop. Let's make this a little bit more readable right here. Has a for loop that is going to run the amount of times as the parameter passed. That's linear. It's a linear time complexity right there. And it's going to call a function the amount of times as the number passed, and pass that same number into a logarithmic time complexity function. And so this is basically saying, well, an O of n is running an O of log n, which means that this function is O of n times log n. And that is quasi-linear time. Now that we have covered quasi-linear, we're going to go on to quadratic time. And as I have said here, this is terrible practice and you would never want to do this. Everything past here is simplified. So quadratic time is pretty easy to understand. It's n to the power of 2. And that is most easily understood as a nested for loop. This is a function that's going to return the maximum number within an array using a terrible practice that you should never use ever, which is finding an element of the array and comparing it to every other element in the array, including itself. Excluding itself within the if statement, but still running an iteration for that. And so this is going to run, this for loop is going to run the length of the array, because as I said, n is going to be the length of the array passed through. And then for loop nested in that is going to run the length of the array as well. And it's going to compare, and it's going to set the max to only what is greater than the previous number being compared. and then it's going to return the max after it's compared to every single element in the array. So this is a pretty simple explanation of the quadratic time. It's pretty easily understood. However, there's one thing that I'm going to briefly touch on, which is a misnomer of a quadratic time complexity of O n squared. This is technically, it looks like O of n squared, but it is not. So nested for loops are not always O of n squared. And the reason is because this is a function that's going to traverse a two-dimensional array and print out each element. So it's going to traverse the array length, and then it's going to traverse the array length of the array within that array, and then it's going to print out that index. The reason that this is not O of n squared, even though it looks like O of n squared, is because the array length and the length of the individual arrays within that array are not guaranteed to be the same number. Even if they are the same number, this is soft-coded so that not every case would be the same number. And therefore, it is O of A times B, or O of N times M, or O of X times Y. It's two different variables multiplied to each other. And maybe A equals B, and in the case where A equals B, this would be N squared. But that is not guaranteed, and so you have to specify that it is A times B. And so this is a misnomer. This is technically not quadratic time of O of n squared. Now we have exponential time, which looks slightly different from quadratic time, but is actually very different. This is a useful function, but at first I'm going to explain it using a useless version of this function. So this function, the useful version, is going to represent the Fibonacci sequence. So you're going to pass a number through. It's going to increase the call count. And in the event that the number passed through is less than or equal to 1, it's going to return the number that was passed through. Otherwise, and this is the main content, it's going to return a recursive call of n minus 1 plus another recursive call of n minus 1. Again, this is terrible practice that you should never use. But each time, let's say you pass 4, is going to call two functions passing 3. And each of those are going to call two functions passing 2. And each of those are going to call two functions passing 1, and those will return 1. And so that's going from 1 call to 2 calls to 4 calls to 8 calls, which is 2 to the power of n. And I'm going to visualize both of these scenarios that I'm about to go over for you in just a moment. But now I'm going to explain the actual use of the Fibonacci sequence, which is the two numbers added before it is equivalent to whatever number you're at. The use case of this function is going to be that whatever number you pass through, so let's say you pass through n, the nth number in the Fibonacci sequence is going to be returned. And so if it's not less than or equal to 1, it's going to return Fibonacci of n minus 1 plus Fibonacci of n minus 2. I'm going to switch over to the visualization so that you guys can get a grasp on this and explain why this is still technically considered exponential time, even though it's not exactly congruent to the first example I explained. So here we have the Fibonacci function right here, and I'm going to explain a little bit about the Fibonacci sequence. So the Fibonacci sequence is going to look like this. And that's going to go on forever. And the way that the Fibonacci sequence works is that whatever number it is currently at is going to be the sum of the two numbers before it. And so 5 is the sum of 3 and 2. 8 is the sum of 5 and 3. 13 is the sum of 5 and 8, and so on and so forth. And so that's this Fibonacci sequence, which now should make sense why the return statement is the number before and the number before that. And so I previously explained exactly how this would unfold, and now I'm going to create a visualization of exactly how this would run line by line. We're going to go through the first most simple example right here, which is n minus 1, n minus 1, and this is not going to represent the Fibonacci sequence. This is just going to be a useless use case that accurately represents 2 to the power of n. Here you pass f of 4. Well, 4 is not less than or equal to 1. So it's going to return f of n minus 1 and f of n minus 1 again. And so that's going to call two functions, each passing n minus 1. Each of these is not less than or equal to 1, And so they are going to pass, they are going to pass f of 2. And that's going to happen 4 times because each of them are going to call 2 functions each. Now each of these is also not less than or equal to 1. So each of these is going to call 2, and I'm not going to write that out. But you can just imagine that this is going to call a bunch of functions, 8 total, passing 1, and then each of these will return. And so that's the end of that. But one function call has easily become 2, 4, 8 function calls, and that is also represented by saying 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. Big O notations, this would be 2 to the power of n, which is an exponential time complexity. Now I'm going to show the visualization right under this of the Fibonacci sequence. Very similar concept, and we're going to show the same parameter. You're going to pass 4, and it's going to call 2 functions. But in this case, instead of calling f of n minus 1 twice, it's going to call f of n minus 1 and f of n minus 2. So this is going to call f of 3 and f of 2. Okay? This is going to call f of 2 and f of 1, and that's going to call f of 1 and f of 0. Now all the functions that have 1 or 0 passed are going to have the first return statement, which is going to return itself. But in this case, we're not using the return value. All we're keeping track of is the call count. Now this f of 2 right here is going to call f of 1 and f of 0, and both of those are going to return. Now this is not congruent with the exponential time complexity, right? Because this is 1, 2, 4, 8, but this is actually only 2, right? So it's technically not getting there, but the rate of growth is still congruent. It's growing in this triangle-like fashion with the growth rate of an exponential function. And so that's why this would be considered exponential, is because this would be represented with quite a complex function. But at the base of it, it is 2 to the power of n, and you can see that by visualizing it. And so this would be considered an exponential function. Okay, here is an aptly named useless factorial function. And I'm going to be going over the time complexity of factorial time. If you do not know what the factorial operator is, I will explain that in a moment, where I'm just going to explain a little bit about how this runs. So again, we have if n is less than or equal to 1, return. And here we have a for loop that runs n times. And so that's linear. So far, this is a linear function, right? Pass n, runs n times. Now, it increases the call count, of course. And then it calls itself recursively using n minus 1. And that's why this is important, because this can get really, really out of hand. You would never want to use factorial time complexity. I will most likely not ever be going over use cases of this because it's extremely complicated. If I can wrap my head around it, maybe I'll try explaining it to you guys. If you guys want to look into an example of a problem that it is necessary to use a factorial time, or maybe not necessary, but is commonly used factorial time to solve, would be the traveling salesperson problem. So if you'd like to look that up, by all means, go ahead. Very convoluted. If you can wrap your head around it, good for you. But I will not be explaining that today. It's really easy to see how this is going to get out of hand. I'm going to go over to the visualizer immediately to show you guys exactly what this looks like. Okay, so this is a little bit complicated, but I'm just going to start out by explaining the factorial expression. The factorial expression, for anybody who does not know, is going to be the product of all of the numbers before it, including itself. So factorial of 3 would be 1 times 2 times 3, which would be 6. And the factorial of 5 would be 1 times 2 times 3 times 4 times 5, which is going to be something. I think it's 120. Is that right? Yeah. Yeah, so this gets out of hand real quick. Faster than exponential, faster than quadratic. And I'm going to show a visualization of the useless factorial function that I had before. So we have a function that takes the parameter n. And then we are going to have the base case here, the if statement. If n is less than or equal to 1, then we are going to return. And we're not going to be using any return values for this. This is going to be a void function, but we're just going to stop the program there. Otherwise, it would run forever. And then we're going to have a for loop. And this is going to be, we'll just say it runs n times. And it is going to, in that for loop, call itself passing n minus 1. And so this is very similar to what we've done before, and it might even look almost the same. So you might be tempted to say that this is exponential or quadratic or one of the other examples. But to break it down simply, we have the function, and we have the base case, and then we have a for loop. Then we have a for loop that is going to run n times. So right now we have O of n time complexity. And in this for loop, it is going to call itself n minus 1. Okay? And this is where recursion gets a little bit complicated. So this for loop is going to run n times, and this function is going to run n minus 1 times, but also n minus 2 times, and n minus 3 times, and I'm going to show that right now with a visualization. This is much worse than linear time. So here is that visualization. So I'm going to do this vertically, actually. So let's say we have f of 4. Nope, we're going to do 3 because that is quite a lot of drawing. So f of 3. Well, it's not less than or equal to 1. This is going to call a for loop that's going to run 3 times and call f of 2. It's going to do that 3 times. So f of 2, and f of 2. It's going to call all 3 of those, and then f of 2 is going to run. It is not hitting the return statement, and it's going to be running for loop 2 times. That's going to call f of 1. So each of these is going to call f of 1. Good Lord. Yep. And then these are all going to return by themselves. But let's scale this a little bit more. So we have this. Let's say we called f of 4. That is going to then call f of 3, which we've already drawn out the contents here, 4 times. So it's going to call that 4 times, and that's going to result in 24 total calls. And then, if you called f of 5, it would call all of this 5 times. So now you understand how factorial is going to get out of hand really quickly. The easiest way to remember this and to be able to determine this mathematically is going to be looking for this rule. So if a function that is passing a variable is running a for loop, or any kind of loop, we'll say, that is running n times. So if you have a linear function, if you have a linear function, O of n, and in that linear function, it is recursively calling itself, n minus 1. That will always be factorial time complexity. So O of n calling itself n minus 1 will always be factorial. This will always be a factorial time complexity. And it makes sense this way as well, because if you look at the call times, it's going to be the factorial of the number passed. But this is a little bit of a representation on factorial recursion, which I might make a separate video on. I'm going to make a separate video on recursion, so I might go over this in that video, but this is the most simplistic visualization that I can manage of the factorial time complexity, which is going to be the worst time complexity that you can muster. Okay, So that was big O notation, a little bit of an explanation into what it is and how you can decipher it from different methods and some of the most classic examples. Some of the concepts that we touched on, the two most important ones was recursion and array sorting, like quicksort, merge sort, and bubble sort. I will be making videos on both of those concepts if you guys would like to understand them more in depth, and I highly recommend that you do watch those or some video on those because those are key concepts, more so recursion than the array sorting. But if you would like to understand this video a little bit better, I would recommend watching one on the array sorting methods, and those will go into depth a little bit farther than we did in this video. If you guys want me to go over specific problems, for example, if you're getting a degree in computer science and you'd like me to go over some example problems to show how to decipher the time complexity of a given function, how it would be on a test, please let me know in the comments and I will make a video on that. Thanks for watching. I'll see you in the next video.